In this video, we are going to address the song class.
Okay.
Now, conceptually, a song is nothing more than a list of notes.
And each note, since we already coded that up, can be aware of its time. So at that point, we really do have a song because we'd have an instrument played at a specific time. So if we just had a list of those, we could play something.
Exactly. We have all of our information put together. Now, in actuality, in addition to this list, we're going to create some additional fields to help describe the song. Things like the ability to store tempo in a song, the ability to describe a time signature using a different set of note blockings, if you will.
Mm-hmm.
We're also going to create a series of events inside of the song class so that the song class can be in charge of watching time pass tick by tick and then firing off events based on what just happened. Maybe a note was just hit, maybe a note was just missed, or maybe we simply passed enough ticks to cause a metronome to fire.
Okay.
So in this video, we want to make sure that we get our fields put together and set up the necessary delegates so that we can have some events happen as time progresses.
All right.
So again, we'll go to the core folder and we'll add in a new class. And let's call this class song. Inside of song, we'll take our subname space, drop that off, and before we jump into the song class itself, let's establish the kinds of delegates that we'll be able to use. There are going to be 3 of them, so I'll note them really quick and then we can code them in. We'll have something called a song handler, which is going to indicate that something happened, but the only item that is relevant is a song instance. We'll have a note handler, and that's going to allow us to pass both a song and a specific note when a given event occurs. And finally, we'll have a note mispress handler to indicate that within a specific song, someone tried to hit a note, they failed, and also pass along what track the note was on.
Okay.
So let's drop these in. Let's begin with song handler. We'll make the delegate. We'll have it return nothing, so it will be a void return type. And this will be called song handler. Now the song handler delegate is simply going to take in one parameter of type song. So the idea here would be something like, for example, whenever the end of a song is hit, the fact that the song has ended, that can be passed along in the form of an event. But in that case, it's not like it ended because of a note. It ended because we reached the end of the song.
Right.
So only the song is relevant, and we will only pass a song along in that case. Now, what if we had an event such as the fact that a note was just hit by the player? In that case, it would still be helpful to have the song, so we can know things like, okay, where in the song are we? But in addition to that, it would be nice to have the note that was actually hit. So we'll make a delegate here, void return type, and we'll call this note handler. And note handler is going to require a method signature of both song and note. So we'll make a second parameter of type note, which we will call note. Since the note is really the point of focus, but song is still relevant in this case because the event is going to be fired by a song class, so we may want to be able to look up what song triggered the event. Now, finally, we have note mispress handler. So this will also have a void return type. We have a name of note mispress handler. And for the method signature, we'll have song and an integer to specify on what track we were trying to hit a note. So we'll say int track. This is an interesting case where generally this would fall under the same rules as a note handler, but in this case, the fact that we're saying that we failed to hit a note, that naturally means that there is no note to look up since we didn't hit anything. Now, we do know that any given hit is going to be given in terms of a specific track.
Right.
So we'll pass along what track the user was trying to play a hit on.
Okay.
And with these 3 delegates, these should nicely describe the different kinds of events that we'll use. So at this point, we can move into the song class itself. Now, the song class is meant to be used as the base class for a few others. In the final implementation, we'll have things such as a song play to handle things like the gameplay and the editor mode. We'll also have a different type of song called a song record to handle free play mode, where we're essentially recording a song live. Now, in this case, we're not going to mark the base song class as abstract, since we'll have all of the necessary fields to store note data. Meaning, as far as data is concerned, we can store a whole song. Even though that song doesn't count time as time progresses, it is still useful as a data storage container. Now, moving into the song class itself, let's start dropping in all of our fields. And we'll begin with the most important, which is the list of notes. So we'll put down a public list of type note, and we will call this list notes. Then we can turn around and immediately instantiate a new note list using the field initializer. So this is really what gives the song class its purpose.
Sure, that's kind of like your sheet music.
Exactly. The song is going to have the list of notes, and that's where we get the idea of multiple notes stored in time. It's up to the individual notes to record at what time and at what track the note exists. But from the song level, we can see that, okay, in this particular song we have 500 different notes.
Right.
Then we can look up the notes individually to get time and track information. All right. Moving on, we also need a field inside of song to store the song's current position. Since the song is going to be in charge of tracking the passage of time, it needs to remember where it is in time. So we're going to make a field called cursor. And this field we're going to mark as protected. It will be an integer field since we're storing discrete tick values using it. And we're actually going to call the field cursor.
So in this case, cursor is synonymous with current tick.
Exactly. It means current tick. You could say current tick of the current song.
Sure.
But we're calling it cursor just as a general term to indicate where the song is at. This would be analogous to, like you said, current tick or even position.
Well, if you picture our song as being a progressing, a progressing timeline full of notes, and you had a single line that just slid down that timeline, and that little single line was your cursor, that cursor would show where you are along the song. That's all we're doing here.
Exactly. We need to store the necessary data for where we are, and so we're going to term that a cursor. Now, the cursor itself is going to be marked as protected, since the song is going to depend on time passing forward one tick at a time. That means if we left this field public, we would end up getting into a scenario where we could mess the song up by forcing it to jump to a random position. So we're actually going to mark it as protected. That way we can still freely use it in any descendant class, but we'll block anyone else from messing with it. Now, the cursor value itself is useful to be able to read that value to use that position to drive things like a rendering engine or to mark off a hit detection in another class.
Sure.
So what we'll do is we'll turn around and we'll make a public property. So we'll make an integer based property called cursor, simply indicated with a capital C for cursor. And we're going to make this property read-only, so we are only going to have a get accessor. Then inside of that get accessor, we will simply return the current cursor value. And then we can end off our brace for the get accessor, end off our brace for the cursor property, and that gives us the ability to read the cursor position, but we don't have to worry about someone jumping in there and messing with the value. Alright, moving on from here, let's put together a series of fields to more accurately describe the song itself. We'll begin with something simple. We'll set a field called BPM to record the tempo of the song. So we'll make a public field of type integer called BPM, and we will default this using a field initializer to 120.
Okay.
And
so by default, your tempo is going to be 120 beats per minute.
Exactly, and this simply helps solidify the idea of a song, so that if you were ever in a scenario where you had multiple songs, you would know that you look at the song to get the tempo.
Okay.
So later in time, when you're setting the speed of your game, you look at the song, you read the tempo out of that, and set the tick rate appropriately.
Well, going back and comparing your song to a piece of sheet music, even on sheet music, they tell you what the BPM on any given song is going to be.
Exactly, so you could look at it as simply as that. We're just marking on this song that it's going to have a specific tempo.
Gotcha. Now, something else that they show on sheet music is the time signature for that particular piece of music.
And that gets a little bit more complicated, but we are going to assemble the information that would be needed to create a time signature.
And this is very similar to what we did inside the Music Engine project.
That's right. We had defined that we were going to use 4/4 time, and because of that, we could then figure out where to place notes and exactly how many ticks we're going to beat, how many ticks we're going to measure, and so forth.
Basically converting the concepts behind a time signature into a value of ticks.
Exactly. Now, to make things more convenient when we're working with songs, we're going to store a series of values that will describe a time signature. And we'll actually go through these item by item, and I'll point out something interesting about all of the ones we're going to drop down. Now, the first of which is we're going to define how many ticks we have in a quarter note. And really, this is going to define the resolution of our song, because we could end up with an arbitrary number of ticks for each given note. If we wanted to go down to a very fine-grained accuracy level, we could give ourselves a very high number of ticks.
Sure.
But in our case, like we reviewed in the Music Engine demo, we decide that the lowest tick we're going to go to, or excuse me, the lowest note we're going to go to is a 128th note.
128th note, which I can't imagine anybody actually trying to bang out on the drums.
And then we calculated that to a specific value, and we took that value and multiplied it by 3 so we could handle triplets, and thereby we arrived at a quarter note value of 96 ticks.
Okay.
And we're going to record that here inside of the song. So right off the bat, we'll know what our overall tick resolution. And once we have the quarter note locked down, we can find the number of ticks in any other time span. A half note would just be 2 quarter notes, and so on. So let's drop down a public field. Again, it will be of type integer, and we'll call this field quarter note, which will be set to a value of 96. So, based on this quarter note value, we can now get into a series of fields that will describe time signature. And we're going to begin with the number of ticks held in a single beat. Let me drop down the field here, and we'll have public int ticks per beat. And we'll begin with that set to 96.
Now that's already the first part. Actually, technically, that's the second part of time signature, because we've just declared the quarter note gets 1 beat.
Exactly. So there's ticks per beat and quarter note being the same. Therefore, a quarter note gets 1 beat. And once we figure out how many beats we have in a measure, we'll be able to tell whether or not this is 4/4 timing.
Right.
At the moment, this looks like we'll have something over 4, since a quarter note is getting 96 ticks, which is 1 beat. So a quarter note gets 1 beat.
So if we're building this by to have default settings of 4/4 timing, what's our next step?
Well, our next step would be to figure out how many beats are in a measure. So we can drop down a field, another integer called beats per measure. Let me grab some spelling on that. There we go. Now, beats per measure, if this is indeed 4/4 timing, we'll have 4 beats in a measure, so we can default this to 4. Now we're going to drop in one last field for our time signature information, and that's going to be called ticks per measure, because in a lot of our game calculations, the engine is just going to care about things in terms of ticks, and a rendering engine might not care about beats, or how many of those you have. It might just want to say, all right, from the left of the screen, how many ticks out do we need to go? Or from the first note, how many ticks out do we need to go? So we'll put down a field called public int ticks per measure.
Now, shouldn't this just be the number of ticks in a quarter note multiplied by the number of beats in a measure?
Exactly. As a matter of fact, let me drop this down, ticks per measure. And so to initialize it here for our default value, we would do exactly that. If we know how many ticks are in 1 beat, and we know how many beats are in a measure, then we can multiply that value against the number of ticks and get ticks per measure. So we would have 96 times 4, which would give us 384 ticks in a measure.
Okay.
Now, the interesting thing about these 3 fields, ticks per measure, beats per measure, and ticks per measure, is that with any 2 of these fields, you can figure out the third by simple mathematic calculation.
Sure.
But for the sake of simplicity, we're going to store them all at the same time so that later in time we can access them immediately. Because if we were in a rendering engine and we only had ticks per beat and beats per measure, we'd have to do the multiplication in that rendering engine.
Okay.
If we store them straight out, it will simplify the code and make it easier to read.
Okay.
We'll simply worry about initializing them all, well, first here with their default values. Later in time, when we start handling the file loading mechanism to load in song files, We'll just make sure that all of them get initialized based on whichever fields are stored. Now, one more field we'll add to the song itself is something called lead-in beats. And the idea is that whenever you load up a song for play, it would be nice if you allowed the user some time to see the notes before they had to start hitting them.
Sure.
Meaning, if your first note starts at tick 0, and your song starts at tick 0, that means the user will have to play that note immediately upon starting the song.
Yeah. And just about playing any song, you hear that 1, 2, 3, 4, and then you'll actually start playing. So it has kind of a musical tie-in too.
Exactly. And that what you were just counting off, the 1, 2, 3, 4, that would usually be the beats for your lead-in time.
Right.
So we're actually going to make a field called lead-in beats. So once again, a public integer. And I'll say this is lead-in, a little bit of casing, beats. And we'll set this to a default of 0. We'll worry about setting lead-in time as we load in or create individual songs.
And technically, that's just an offset. That just slides your song off the timeline, slides it forward, I guess you could say, X number of beats so that the player has some time to see it marching toward them.
Exactly. And we'll leave this configurable and listed in beats. Beats to make it make sense musically, and then we'll calculate it as an offset. So that way we could say that if you had a 4-beat lead-in offset, then that's what you could imagine, a count of 4 before you have to start playing the song.
Mm-hmm.
The other nice thing about that is we could actually implement that another way. We could store all of our song files with a series of empty ticks at the beginning, meaning make our first note always be maybe one measure into the song.
Mm-hmm.
But the problem there is it makes it less configurable song by song. You wouldn't... how am I trying to phrase this? You wouldn't be able to edit the songs as easily.
Okay.
It makes more sense for storage to say that the first note is always tick 0.
Mm-hmm.
It makes it easier to handle the song. Things like edit mode could then place the first note on the cursor to begin with, because you don't need to lead in time in edit mode.
Mm-hmm.
So we'll leave this configurable to the song itself. All right. Now that really takes care of all of the data fields that we need inside of the song class. What we're going to do now is define a series of events. So we'll put some of our delegates into action, and we'll list these events so that the song can also be used as a kind of processor.
Mm-hmm.
It's like a time processor. And then as time passes and it watches notes, we can cause certain things to happen. So let's begin with the first event, which is going to be the beat event. We'll make the event public. We'll note the fact that it's an event with the event modifier. This event, the first one, is going to be of type song handler, so we'll only have song information, and we'll call this event beat. Now the beat event is, you could think of it as like a code-based metronome.
Mm-hmm.
It's very much like the update method inside of our original music demo.
Sure, every beat this is going to get called.
Exactly. Or you could, to be more specific, you could say the music demo before we started subdividing ticks.
Okay.
The initial implementation had our update method being called as a metronome, once per beat. Of course, later we subdivided that. But here, if you want access to that happening, because if you remember in the music demo, we had to use modulus to figure out what our beat ticks were.
Right.
Here inside of the song, we'll simplify this by simply firing a beat event.
Okay.
So someone watching the song can implement a metronome much more easily. Now, as we're declaring each of these events, we're also going to drop in an empty anonymous method just to follow the pattern, which will allow us to call any of these events at will without having to worry about whether or not they have been hooked up with a listener. So, beginning with beat, we'll say that it is immediately equal to a delegate. So we'll use delegate to define our anonymous method. The method signature is going to be the same as our song handler signature. So one parameter of type song, which we will call song, and then the method body will be a set of empty braces. Now let's take this beat event and let's duplicate it. We'll make a second song handler event, but we'll call this event ended. And the idea is that once the song sees that it has reached the last note, or maybe an amount of time past the last note, we can fire off a song ended event.
Okay.
And then that can be used in the context of a game to trigger the score screen. But again, a case where we don't have to watch the tick value inside of the game, we just wait for the song to tell us that it has ended. Alright, next up we have a series of note events. So we'll put in, once again, public event. The type will be note handler. And the first of these note events is going to be note play. And then while we're setting this up, we can jump in with our delegate. We could say we'll have an anonymous method, so we'll have delegate. We need to match the method signature of note handler, which is a song parameter and a note parameter. For the sake of time, I could just copy this signature and paste it into our anonymous method, and then give the empty method body. Now the purpose of note play is going to be to write our game in a way that is a simple music player, meaning regardless of the user's input, simply fire an event whenever a note would need to be played audio-wise.
Okay.
So regardless of whether the user hit a note or missed a note or tried to hit a note, the idea is every time the song sees a note go past the cursor value, it'll fire this event. So we could make a very simple music player inside of our game by simply playing the note's value every time note play fires. Alright, next up we have note hit. It'll be the same type. It will also be a note handler. So I'll copy and paste note play. And we'll call this event note hit. Now the idea is that our song class is going to be able to take input in the form of arbitrarily timed note presses. And those note presses, if they happen to correlate with our cursor value, and a tick at that cursor value would indicate that we hit a note. Of course, we could implement a threshold value, so you're given a bit of forgiveness in between the
You'd kind of need to. I don't know if anybody's going to be good enough to hit a note on a specific tick at 60 frames a second.
At that point, some of the inaccuracies in an analog input device would prove to be a problem. But the idea is so you could say with a set of factors, including cursor, note, and a threshold. We run into a scenario where the user hits buttons on their controller, and if that happened to be in time with our song and a note in the song, then we will have successfully hit a note on a
So then we'd
track.
fire note hit.
So then, yes, then we'd fire note hit. So that way, but the idea is that note hit would only fire in the case of a successful note hit.
Okay.
Not when a note passed by and got skipped, or not when a note was attempted but missed.
Okay.
Only in the case of a successful note hit. So, moving on from here, we have note miss. So I will once again duplicate our note hit line. We'll call this note miss.
Now, a second ago, you mentioned 3 separate circumstances that could happen during gameplay. One is where the player hits the note, and we'll just assume that that threshold is there. Either way, they were successful in hitting that note. Another one would be if they actually struck their instrument and played the wrong note at the right time. And then another circumstance would be if they, hit nothing and just watch that note go by.
Right, this would be the case that they did nothing.
Okay.
They saw the note, and they, for whatever reason, failed to hit it. Maybe they hit an entirely different track. Maybe they just hit nothing, and the note passed by.
Okay.
The moment the song notices that a note has passed out of the hit threshold and has not been hit, it can count that note as being missed.
Okay.
So we'll fire off, and in that case, we'll actually fire off an event just in case we want to do something in addition, maybe an effect, maybe change the color of the note. You could do any number of things in that case. Now, one more event that we need in relation to notes is going to be note mispress. And the idea is that this is a case where the user tried to hit the note, they hit the right track, but they hit it at the wrong time.
Okay.
They either hit it, generally that would be if they hit it too late.
Okay.
Because if they hit it too early, in this implementation, we're
They
not
missed
actually...
the previous note.
Right.
Oh.
They missed the previous note. Technically, they hit nothing.
Right.
The idea is that it's just a miss in general.
Okay, so this is basically you hit it too late.
Exactly. So we'll make this a public event. This will be a note mispress handler, and we'll call it note mispress. And let's see, looking at the spelling here, looking at it, we don't really need two S's in there for Miss Press.
No, we don't. That would be if Miss Press was actually married to Mr. Press, or
So, just
Mr.
glancing.
Press's daughter.
So looking at, we'll correct that here and in the delegate definition as well. So that way we have note mispress handler. We'll call it note mispress, and we'll set it equal to another anonymous method. So we'll set it. We'll use delegate. We'll pass in the song from which we missed the note. So we'll have a parameter called song, and it would be helpful to say what track they were trying to hit, though we don't have a note to gather the track information from.
Okay.
So instead, we'll directly pass an integer called track. So we're saying that, okay, even though there wasn't a note there when the user tried to press it, this was the track that they were trying to hit. And then we can put our empty braces out to the side.
Okay.
So that way, in any event where the user hits a note and there's no note within the threshold, then we can trigger off that event.
Cool.
Now, looking at this, I believe that is all the fields that we'll need inside of the song class.
So from here, we'd actually be ready to take a look at the method layout for this class, but we're not going to do that in this video. This video's gone on for a little while, so we're going to kind of take a quick break, and then in the next video, we'll take a look at the method skeleton and implementation for this class.